Hello, my name is Markus Niemitz. I'm a PhD student at the University of Edinburgh, and today I would like to talk about the idea of embracing collisions in robotics research. I would like to start my talk by emphasizing that the vast majority of physical, biological, and chemical agents collide with one another, whereas examples range from colliding bees to humans playing bubble soccer. In the world of conventional robotics, we do quite the opposite. We avoid collisions to prevent damage to the robot and its surrounding. However, it was our decision to design robots the way they are. We have chosen materials from a list of materials and environments from a list of environments that made robots fast and reliable, but their collisions also destructive. So what happens if we choose different materials or environments? Before we answer this question, we should know why we want robots to collide. Collisions contain rich information about all sorts of physical interactions, whereas we believe that we have only scratched the surface of their potential. There is some immediate reward when one starts working on colliding robots. For example, we no longer care about collision avoidance, a robot skill that has taken many of our resources. We also benefit from the nature of collisions. That is, for constrained environments, the number of collisions increase with the number of agents. This is very useful for collision-dependent robot behaviors and applications such as collision-triggered search, collision-triggered localization, or collision-triggered mapping. If we make changes to the materials and environments that our robots are made of and operate in, we can develop robots that embrace collisions. In soft robotics, a change of material led to a new class of robots. Such robots embrace almost any kind of physical interaction. Besides material choice, I found another opponent of collisions, that is, frictional resistance through the robot environment. Therefore, I decided to make robots frictionless by modifying their environment. Robots hover on air cushions and move by using electromagnetic actuators. HoverBots consist of a single PCB and a battery. There is no manual manufacture required. Robots can be ordered populated since all components are surface mountable. The assembly consists of plugging in a battery to the robot. HoverBots move in 2 dimensions, communicate globally via infrared, and detect collisions, successful movements, and rotations with a single Hall effect sensor. We are currently investigating how we can utilize HoverBots' capability to detect collisions to collectively map an environment. My name is Markus Niemitz, and I thank you for your attention.